where these revelations came from. And that makes it much more personal, which is why the original series was actually called The Personal Journey. But either way, this new series is fantastic. And so why I do this panel is I want to share with you this little journey of science, because we can discover some amazing things. I don't know if you heard last month, but NASA just announced the discovery of 750 new planets in one fell swoop. That almost doubled the number of planets that we know about outside of our solar system, which is an amazing feat to me, because when I was in elementary school, I had teachers tell me, we will never find planets outside of our solar system. We know they have to be there because, well, we know how stars form and how planets should form based on our own solar system, but they said it would never happen. Science has done the impossible, and that makes us mighty. Oh, come on, no one gets that reference? You guys need one more Firefly, too. This is stuff you can watch Cosmos, watch Firefly. All right, whatever, it's an amazing journey. And I want to share this with everyone, even in a small part where it's something trivial. I mean, yes, we're making fun of science, but I hope that seeing that science can be an amazing journey, even on this trivial scale, is something that is really exciting, and I hope other people kind of get into it. So, yay science. So, okay, let's go ahead and get started with some old favorites. As every year, I take a couple old ones, and then I add a couple new ones, so I think I got 3 or 4 segments from previous years in here. So I'm going to start off with Trigon here, and I think anyone that's seen Trigon probably did this and scratched their head as much as I did. Got it. Yeah, there we go.
So you want to try? It's pointless no matter what caliber pistol you use. Like trying to stop a car from ramming at 120 miles an hour. You failed it twice already. Even your puny brain can realize my son's fist is a force to be reckoned with. Or do you really believe you still have another one? This is your last chance to run. Although no matter how fast you are, within the next few minutes you'll be smashed into tiny pieces. Now pay attention, because as a courtesy I'm going to lecture you on just what a stupid fool you really are. Using this technique. My human instinct special course. Go have the squiz. Enjoy being a hero for a moment, then die in a most humiliating way.
Not quite, Doc. I have one left. Could be my special one.
6 bullets, or 5 bullets versus car-sized fist. Let's see who's going to win. So I like doing diagrams because anytime you've probably ever done high school physics or anything, they always say draw a picture and draw vectors and stuff like that. So I did it. So on the left here we have 3 passed out women. You can tell because they have Alexis on their eyes. And then we have Bash and Big Bulbous Headman with his giant fist of doom. No, this is not quite to scale. Alright, so starting off we have, these are all very kind of rough numbers. I mean, obviously I didn't take a meter stick to Trigon Land and figure out exactly the distances, but I tried to figure out as best as I could. So I gave it about 60 meters, which is really actually a pretty big distance. It's almost 200 feet for that fist to cover there. He said it was going 50 aisles an hour. I don't know what an aisle is, but I'm going to assume it's a mispronunciation of mile. I'm sorry, I forget what units he said, but I converted it to meters a second because that's what I work in. A mass of a car should be about 2,000 kilograms. And I'm going to assume that Vash kind of has the absolute best physical performance of any human on the planet, and he's running at about 10 meters per second, which is pretty fast. So up in the top left here, you can see what time it is. And this all happens very quickly, despite the bullet time going on. And the way I'm going to treat this is, originally I thought of this 6 years ago when I first was like, hey, what should I do for this panel? And I got really caught up in the fist is spinning, and it's going to act like a centrifuge, and all these fancy forces. And after sitting and thinking about it for 4 years, I finally realized, no, you can kind of just treat it as a momentum problem because it's all along the one axis. So that's what we're going to do here. So first off, at time 0, the fist fires, Vash is running, and he's pretty much right ahead of it, because if he's going to deflect it, looking at the women from straight on, he deflects it to the right, which means he's going to need to be nudging it from the left. So he can't be, shooting it from the direction he's trying to nudge it, otherwise these would be magic attractive bullets. That makes no sense. So he has to at least be in front of it by the time he starts shooting. So at time 0, I have him right in front of the fist. And then for anything that has momentum, we're going to do it times the momentum as the mass times the velocity. And we can just plug in some units here. The overall momentum of the fist is about 100,000 kilogram meters per second. And I've got this funny little eye with a hat on it. It means it's a unit vector. It's going in this direction. I'm going to define positive as going to the left, just because I don't want to have to deal with negatives here. So anyway, that's a lot of momentum that we have to overcome. So let's start shooting. And as I say, this is going to be at position 0, 0 is where the fist is. So here's when the first bullet is fired about 1/5 of a second after the fist goes shooting off. So we have initially the momentum of the fist is 100,000 kilogram meters per second, going at 50 meters per second. Vash fires the first bullet, and now we're going to look at the momentum of that. Well, it's going about 400 meters per second for that type of gun, and it weighs a whopping 0.02 kilograms. Woo, that's a bunch. So the momentum from that, 100,000 now compared to 8 for that little tiny bullet. But either way, the bullet's going to lodge itself in the fist, and it's going to impart that momentum and push it in a certain direction. And because it's not straight on, it's going to push it off to the side. The angle Vash is going to make is he's traveled a certain amount of time, that 0.2 seconds. So we can figure out that angle, which would be the tangent of 250, at an angle of 2.3 degrees. Very steep. So we add all that in, and we get the momentum of the bullet is going to be pushing it with just that little bit, that 0.32 in the positive y direction. And then adding that into the fist, we now have the fist having a momentum of 99,992.01, still in the same direction it was going. Let's pick up a little bit of momentum in the y direction, getting away from those poor helpless people. At this point, though, it would be going 49.99 meters per second, still towards the people and barely at all really away from them. But that's okay, because we still have 4 bullets to do. And also, as the angle gets steeper, it's going to push it more in that y direction, so maybe there's hope. So let's do it all again. Faster. So the fist has momentum, the bullet has momentum. The bullet's at a steeper angle this time, so it imparts a little bit more momentum in the y direction, which gives it an overall momentum after the second bullet of really only 1.12 in the y direction, and it's still not getting there. And it's still pretty much going at the exact same speed. One more bullet. Fist has momentum. Something bad happened. It's back. Bullet has momentum. It's at a steeper angle, so it pushes a little bit harder, but not really at all. So let's do it again. Fist, bullet, steeper, a little bit more momentum, but still almost 100,000 right at the people, and still losing pounds. I think this is the last bullet. I should put a number on here. What the hell? I don't know what's going on. Fist, bullet. Really steep angle at this point, because the fist is almost about to hit those people. And now the fist has a momentum at the last second, and this actually kind of is to scale on the graph, at least, that people are going to think it's not to scale. But still, most of the momentum is right at the people. It picked up a little bit in the y direction, not bad, but not quite enough to get it to veer off course. Because Bash is now saving his last bullet, and it's still headed right for the people. So, that might, but we don't know because they don't tell me. So at the very end, it is right to people there, and it still has almost all of its momentum right at the people there, and they go squish. Bash is not the hero he wants to be. So final numbers are it hits having only lost 0.02 meters per second after 5 brutal bullets. All right, that's sad. Let's move on. Samurai 7, anyone seen this series? Yeah, it's pretty good. Kind of an underrated series. I don't see a lot of people getting into that one, but it was a remake of, Seven Samurai, but just in anime form and very cool. I highly recommend checking it out if you've got the time. But this is from an episode where the big bad guys are coming for the 4 little villagers that the 7 samurai are defending, and they get really inventive about how they're going to defend the village.
This is no idle threat. Drop your weapons and cross the bridge one at a time. Fire! Fire!
Right in front of that. Obviously, they had no aiming mechanism there. But this is one of those things I look at and just go, oh my gosh, that is so fully, system, and I can totally do that. That's high school physics. So I saw that and I knew that this was going to be a segment here. So let's break that down. Is they have a giant tree, and I mean this really is a giant tree, and I'll get to the dimensions here shortly, but they had all those little people on the ground, and they showed the big ballista overall, so I took one of those little people and stacked them up to figure out just how big that tree would be. It's like a California redwood type tree. I mean, it is a big darn tree. So they put it on this ballista type thing, and they used a part of a cliff. Now, it's hard to explain here because it took me several times to watch because it seems like they're up on a cliff. It's all Anakin, I have the high ground. No, it's actually just a gorge, and the enemies are actually on the same level. So they have this gorge between them, and they use a big chunk of the cliff face on that gorge to attach it to some ropes, and they try to use that to propel the giant tree. However, that does tell me one thing. Because that giant piece of rock, the fastest it's going to accelerate is the speed of gravity, so 9.8 meters per second squared, which gives me a maximum acceleration for that tree. So it doesn't matter that they have that big iron spring arm, because if it was going to pull the tree any faster, the line to the big rock would have lost all the tension, and that would have been completely worthless. Maybe they were done, but I'm going to assume that it didn't because I didn't see that lose any tension. So I'm going to go with a maximum acceleration on that tree of 9.8 meters per second, and let's figure out how far it can really go. So On this one, we know that the acceleration of gravity is 9.8 meters per second squared, and again, counting the little people, long versus tall on that, I figured out that it was going to be released at a super steep angle of 1.3 degrees above the horizontal. And he's basically shooting it straight flat. Good job. I don't know. So let's get some just general kinematics equations here. We can figure out the final velocity of the tree if we know the initial velocity of the tree, which was 0, the acceleration and length of it, which was 75 meters. Again, really tall tree. That's almost 200 feet, a little bit more actually. So we plug all that in, and we get its final release velocity is about 38.3 meters per second, or just over 85 miles an hour. This is looking pretty good. So let's take a little bit more looks at it though, and figure out how long is it going to take for it to make that full arc. Is it really going to get way out there? Well, again, there's an equation for that. So we plug in the final velocity, the initial velocity, the acceleration for gravity, and we can figure out the time. So we solve for t, plug things in, and it's in the air for a whole, almost 1/10 of a second. Where's it really going to go in 1/10 of a second? Yeah. So the full arc, that was just at max height. So in 0.17 seconds is when it would have hit the ground again. So in that time, we can get distance traveled. Turns out it's less than 7 meters, or about 200 feet. Not very much. From that, we can also figure out what its max height would have been. If you're ready for this, lay down. It is going to get a whole 1.3 feet higher than its initial release. Not the best weapon ever. It just goes, okay. Not the best weapon. All right, so Comet. This one was from the last episode of Avatar: The Last Airbender, and there's a comet that flies by, and this is a really short clip. I feel bad at having really long clips, and now I'm like 20 minutes in, and oh, whatever. But now this is a short clip, so we can do this one. This is just to let you know what series it's from. It has nothing to actually do with whatever. Here comes the comet. There goes the comet. Yeah, see, it would have been really lame if I just had like 2 seconds. I go, yay! I had to do it a little bit more. Now, how many people have actually seen a real comet here? Not a meteor, but an actual comet. Looks like a fair number of people. Since you're close up here, what does a real comet actually look like? So it's moving like that? Not really. A real comet hangs there in the sky. It's moving very, very fast, but it's also very, very far away. Kind of like a plane. They just seem to float there. You have questions?
The fact statements on the comets that the first version said that it was because the comets slid the atmosphere.
Why did they do my work for me? Well, I'll prove it here. All right, so yeah, normally comets are very far away, so they don't look like they're moving fast. For it to be moving that fast, it would have had to come very, very close to the surface of the Earth. So I was asking how close. Apparently there was an answer, but so whatever. Yay, pictures, because you always have to draw diagrams. So we have the sky, which is blue, except in Avatar, when it's red. We have the ground, which is green, at least in my happy world. And what we need to do is we need to figure out kind of where that comet started and where that ended up. So I think it started off probably about 45 degrees above the horizontal and ended probably about 15 degrees above the horizontal in that 3 seconds. So I can draw that in here as those line of sights to the comet. Ooh, now we started getting triangles. Everyone loves triangles. So let's draw in another parallel line to complete the triangle here. So now we know that that upper left one is also 15 degrees because, alternate interior angles and all such that. And, in flat geometry, angles inside the triangle add up to 180, so we know the other one is 135, if that matters. And then we can draw in some other lines here to figure out what we need. So I have the h, the height above the ground the comet's going to be at, and then the distance to the comet from the observer. And a comet is traveling about 50 kilometers per second. That's really fast. So in 3 seconds from that clip, it would have traveled about 150 kilometers. So now I think we have enough to actually start doing some math here, and using the law of sines, which I get super excited about. I never get to use the law of sines.
Law of signs?
Yeah. Law of sines, usually I'm using like the Pythagorean theorem, so yay, law of sines. But from that, I was able to figure out the distance to the comet from the observer was about 210 kilometers. And then we can use the good old Pythagorean theorem here, or just, some sine and all that. And we can figure out that the height above the ground of that comet is 54.9 kilometers. That's fairly high, but does anyone remember the X Prize that happened about 10 years ago? The X Prize. It was a challenge for a commercial space agency to send a probe up into space, land it again, and then launch it again within 1 week. There was one about 10 years ago. It was interesting how they defined space, because they say space starts at 100 kilometers. So definitely this is inside our atmosphere here, but how inside our atmosphere? So here's a diagram off the right of kind of height. You can see Mount Everest down there at the bottom. It only gets up to about, I think, 3-point-something kilometers. That first line there is 6 to 20 kilometers is where planes fly. 50 kilometers, weather balloons are a little bit below that. Meteors burn up in our atmosphere below 65. A little bit higher at about 100 where space starts. That's where you get just enough atmosphere for those energetic particles to create aurora. The space shuttle usually flies between 100 and 300 kilometers. And obviously that's further than we need. So where is the 54 for the comet? Way down here, where meteors are burning up. Well, what happens when a big chunk of something gets that low in our atmosphere that's actually big? Well, ask Russia. So last year, this meteor entered the atmosphere over Russia. And it was really cool, like a smoke trail, and like 3 videos out for 50 square kilometers. So yeah, that was fun. And that was small. I hope they're not swearing in Russian and I'm showing that. So yeah, I mean, definitely a dangerous thing. And that was something the size of a tiny car. When I did this panel actually at Archon about 5 months ago, one of my friends was there. She's a PhD astronomer, and I showed this clip, and she goes, "I have a piece of that in my pocket!" And she really did. Is that she works for an astronomy outreach group, and they've been doing a big fund drive, and there's a guy who collects pieces of asteroids and stuff, and he donated a bunch, and she got one. So she actually had a piece of something that blew up over Russia. Yay! Pieces of it did. But either way, that's not very big. This was something really actually pretty small. Now we did something a little bit larger, about the size of a bus. Well, that happened in the early 1900s over Siberia. And it flattened trees for a 100-kilometer radius. Stripped them bare. Now a comet would be even larger. It would be the size of a small city. This would be even worse. There's lots of giant craters all here. There's Crater Lake, there's Crater National Park. Yeah, there's some big craters. Okay. Well, the other thing about this is that that's really, really close. And people have been freaking out about this asteroid, 9942 Apophis. Anyone heard about this one? Yeah, it's the, oh no, doomsday asteroid. It's going to come really close to Earth, 40,000 kilometers in 2029, and if it passes at just the right distance, it's going to get a little gravitational boost, and in like 100 years, it's going to come back and kill us all. But as I say, this is 40,000 kilometers away from Earth, and that white line there is that 90% confidence interval. So we are pretty sure it's going to miss us at this point. But people are freaking out at 40,000 kilometers. Is the distance from Earth, the little green dot in the center, to the blue line. Now scoot that little blue line to 54 kilometers over Earth, and that uncertainty, we wouldn't have it. If that was the case, the Fire Nation would be the least of your worries. We could develop a space program really, really quickly trying to stop the comet, which would not do anything. Not even that, is you still have all the energy coming right at you. You are still, nuking it is a bad idea, despite what Armageddon said. So since I'm feeling spacey, I'm also going to do one from Kenshin about space. And this one's going to be really slow and boring, I'm sorry.
Da-dum. Da-dum. Da-dum.
Oh, it's an eclipse. That's what's happening.
Why is it so slow?
Good question. Intention's just sitting there going, hey, let's stare at the sun. And he just keeps staring. Yes, you wear special glasses because you will go blind. Even during an eclipse, the sun is still very bright, even that little tiny bit. So yes, do not ever pull attention. So here's the thing about that, is Tension stood there for, well, about 30 seconds for it to completely cover the sun. Right, he's going to be blind, but who cares? I mean, he stood there for 30 seconds, and that was probably the most boring thing I'm going to show you today. But there's one other problem. A real eclipse takes about 2 hours. So maybe they sped it up, but still, think of that. He was sitting there for 2 hours dumbstruck. So in reality, no, the anime moon must be moving a lot faster, because I really don't expect Tension to sit there drooling for 2 hours. So the whole eclipse in Tension would have really only taken about 1 minute, which means it's moving about 120 times faster. If it's moving that fast, it's got to have a lot more potential to be kept in orbit. So I'm going to pull some numbers out here. A real orbital period for the moon is about 29 days, 12 hours and 44 minutes. Divide that by 120, and we get that the moon is now orbiting every fourth of the day. Some other numbers I'm going to play with. We got the mass of the Earth is basically 6 times 10 to the 24th kilograms. The mass of the moon is 7.36 times 10 to the 22. And the distance to the moon, and this is at perihelion, the closest point. And when it's at its closest point, it's moving the fastest. I'm trying to give it the best chance I can here. Really, is 3.63 times 10 to the 8 meters. So from this, we can start getting some other important facts by playing with Newton's revision to Kepler's third law, which is the equation I've shown up here, and I've defined all the variables here. But we have to play with some variables to make this work. We obviously can't change the period, because then that would change the amount of time it would take to cover the Earth or cover the sun. We can't change the distance, because if we change the distance, then the moon would either, if it's closer, it would be covering the sun entirely, and you wouldn't get that nice little ring effect it showed. If it was further away, well, then it wouldn't cover the sun completely at all. G we can't change, because if we start changing the fundamental gravitational constant of the universe, it falls apart. So let's not do that. And we don't want to change the mass of the moon, because if we change the mass of the moon, well, then the Earth would be orbiting the moon and not the other way around. So the only thing that we are really going to be allowed to play with in this equation to make this work is the mass of the Earth. So we can solve for the mass of the Earth here, start by rearranging it, get the masses by itself. We can plug in the period that we got just a couple minutes ago. We have still the semi-major axis, the distance to the moon, the gravitational constant we can't change, and the mass of the moon, which gives us a mass of the new Earth of 1.33 times 10 to the 33rd kilograms. That's big. So let's put that into some kind of context, like the surface gravity. So we can get the surface gravity from the little equation here, and for normal Earth mass, this is going to be that 9.8 meters per second squared, and it's going to get a little bit bigger here. So we plug it in, and this new anime Earth has a gravitational acceleration of 2.2 times 10 to 12 meters per second squared. Again, divide that by the actual gravitational pull acceleration, and you find out that you are going to weigh 220 billion. This is going to hurt my legs when I play DDR. All right, so this was all the old material. I'm going to start on some new stuff now. I'm halfway through the good timing. So this comes from Van Red. And in this episode, I don't have a clip for this one because it was too hard to put together. But there's lots of bad guys. So what do? They hide inside a planet because they can't be followed into a planet or something. But apparently this is a special planet because this planet is turning into a star. I don't know if they know what the word planet means, but planets don't turn into stars. What they probably mean is that it is a protostar, a star that has not yet started fusion, but is really close. And it has to be really close because their plan is to fly into the center of it, shoot it with lasers, and cause fusion to start. And then they will run away from the blast wave, and the bad guys will forget to or something. Which is actually happens in that episode. Is they turn the star on by shooting the core with lasers. Lasers. So in this, as they're flying in, they give me one key piece of information, and they tell me that the pressure is 2.31 gigapascals. Woo, giga, that's a big number, right? Well, let's find out. First off, if it's a protostar and it's about to start fusion, it has to be at least 13 times the mass of Jupiter, because if you're 13 times the mass of Jupiter, you can just barely do fusion. And only not hydrogen fusion, but a specific type of hydrogen fusion called deuterium fusion, which is heavy hydrogen. Hydrogen normally just has the proton and an electron orbiting around it, but heavy hydrogen has a proton and a neutron. It's a little bit easier to fuse. So brown holes can just barely fuse deuterium. So I have a minimum mass here, which is going to be the least amount of pressure. Again, I'm going to give it my best shot and try to give them the best possibility of making this work. But as I say, it's about 13 times the mass of Jupiter, which means it has a minimum mass of 2.5 times 10 to the 28 kilograms for this protostar that they think is a planet. Also, these brown dwarfs, they tend to have about the same radius as Jupiter, so 7.15 times 10 to the 7th meters, which means we can calculate the density just as mass divided by volume, and we get that the average density of the star is going to be 16,000 kilograms per cubic meter, which is fairly high. All right, now here's where it's going to get really handy. So I'm going to, why is that hanging down there? I shouldn't show you yet, but it's okay. A real stellar interior, we want to try to figure out what the actual pressure in the center of a real star is going to be like. So I'm going to start off just talking about a density gradient. So the pressure at a given point as a function of that radius. This is calculus, but you can kind of simplify it just by saying it's the change in pressure as it goes on the change of radius. So I have the pressure at the surface minus the pressure at the center, divided by the radius on the surface minus 0. Really, that should be the radius of the center, but the radius of the center is my starting point. It is the 0, so I can just plug in 0 there. And we're also going to simplify this because the pressure at the surface, well, that's the edge of the star, so it has to fall off to 0 there. So really, this simplifies things really nicely to just negative P at the center, the pressure at the center, divided by the radius at the surface. Yeah, that's nice and simple. Let's make it complicated. Let's set it equal to the equation for hydrostatic equilibrium, which is not really that good of a thing to do because this is still a protostar, it's still technically collapsing, which means it's not hydrostatic equilibrium, but for short time scales, we can get away with it. So I'm going to set it equal to G, the gravitational constant that we just got to play with, times the mass of the star, times the density, divided by the radius squared. So I plug all these numbers in after solving for the pressure at the center, and I get this big fancy thing here that's been scaring me in the face for a while. And then I can press the button again, and I get the real central pressure of the star is 1.6 times 10 to the 17th pascals. Now, if you don't remember what they said, it was 3.21 gigapascals. Giga means 10 to the 9th. So we are still 8 orders of magnitude off here. We are off by, what is that, 100 million? Yeah, a factor of 100 million there. So really, they really couldn't have been that close to the center of the star if it is that far off on pressure. So let's try to figure out really how deep were they? Well, let's make a graph, because graphs, I haven't done that yet. Well, I kind of did, I'm going to try again, but this is a real graph with not pretty pictures. So I'm going to start off on the left, on the y-axis, that's going to be the pressure. Then I'm also going to have the radius of the star, and we've kind of already defined 2 points here. So we have the center of the star. The radius being 0, but we calculated the pressure there is 1.67 times 10 to the 17th pascals. And then we have the other point on the surface of the star, which is 7.15 times 10 to the 7th meters out there, and the pressure is 0. So I have this nice straight line we're going to try to use to model. Because now we have 2 points. Hey, we can get a line. I can figure out the slope, write the equation for the line, plug in what they told me the pressure was, and then I can get the radius they must have actually been at. Yay, high school math. I know I'm cheating again here because real stars don't look like this as this graph because the density isn't constant there. A real star would look like this, where at the surface, the density isn't that high, so if you go a little bit deeper, it's not squishing that much, but when it gets to the center and it starts getting really, really dense, moving a little bit further is going to put you under a lot more weight. So it starts to stack up really high as you get to the center of the star. But is it going to matter? Well, as I said, I figured out the equation here. So the pressure is a function that is negative 2.33 times 10 to the 9 times the radius plus 1.67 times 10 to the 17. And as I say, I can plug in the pressure they give us to figure out the radius. And here's where they are. They are barely under the surface of the star here. So instead of being able to shoot the core with their lasers, they're shooting nothing. They're shooting the outside of the protostar, barely hiding in the atmosphere, which kind of blows their entire plan as if it made any sense anyway. No, because to spark and explode, you have to have oxygen, which does not exist in large amounts in the universe. You have it here because of weird things that happen with the formation of the planet and getting locked up. So, that's that one. Next one, initial D. This comes from the second episode. There's somebody here, I think it was here last year, that somebody gave me the idea. It's from episode 2, and I'll go ahead and show you this. Drifting around corners on a mountain pass while delivering tofu, and his dad is trying to teach him how to be a really good drift racer. He gives him a cup of water and says, "Don't spill this," because that's going to help you figure out how to do it or something. But the interesting thing about this is you can figure out what speed he's going around these curves because of the forces involved on the water. So what I did is I took some fuzzy numbers again on this cup. Because the cup is probably about 4 inches tall, and that 4 inches across. And the water kind of makes, it goes up about 1.5 inches, which gives an overall angle that we can be able to play with here in a second. And that angle is going to be created by the sum of the forces here. So we have the force of gravity acting down, and the centrifugal force outwards, which is balancing the center seeking force there. So I can put these in here and start figuring out what's going on here. And that's going to give you that angle that the water is going to end up making here. So I set all this equal, and I'm wanting to solve for something here. I did this like a week ago, very hastily. Anyway, yes, so I get the sum of the forces, and then I put in that the sum of the forces is also equal to, as we just said on that second line there, the force of gravity divided by the cosine of the angle is equal to the sum of those forces. But what I really want is the centrifugal force. So here's where it's going. So I set all that equal. I'm going to square both sides first, get away with that nasty square root, because who likes those? Even though now we have a bunch of squares hanging out everywhere. I want the centrifugal force by itself, so I subtracted off the squared force of gravity, and now I've got the square roots again. Because I unsquared the centrifugal force there to get this equation there, and this one gets really heavy. Right. And then we have the centrifugal force is the force of gravity squared divided by the cosine squared minus the force of gravity squared. I need to substitute in what the centrifugal force is there, which is mv squared over r. Oh my god, more squares! So I need to divide out the m and r there, so I do that. Right, so yes, this is getting big and nasty. And now I need to get rid of those force of gravity, because the force of gravity is m and g, so let's substitute that, and oh my god, more squares. And I want to factor out that m squared that's in those two terms on the top there, which gives me an m on the outside and m on the bottom. They cancel out. So now I have this, and it's starting to get simple, but I still have that square over there. So even square roots within square roots. Goody. But at least I solved it. Remember at the beginning I was saying how science is a journey, and you get to the end and it's a really good, this is a really good feeling. I solved an equation. I'm excited. Anyway, I've got the velocity isolated now, and it's really actually, the equation looks bad, but there's only three things going on here. The radius of the turn that he's taking, that angle that the water makes, and the acceleration due to gravity. So we have to figure out what that radius of the turn is. Well, if you watch the beginning, the opening series, he's making hairpin turns around these corners. They are a mountain pass that just basically winds back and forth. So I'm going to be generous here and say that the turn he's taking has a radius of about 100 feet or 30 meters. Let's start plugging things in here. I have the radius, I have the gravity, I have that angle that I figured out, and we get that he's going about 60 miles an hour. Which doesn't sound so bad. And actually, I was talking to one of my friends who knows stuff about cars last night, and he's like, hey, there was that little thingy, which was the warning indicator. So he had to be at least going 100 kilometers an hour, which is about 60 miles an hour. So actually, things are working out really well for a change. So let's see what's going to happen with this. Well, we have that centrifugal force, which is the one that's going to be pushing him outwards. But what's going to be holding him on the track? So let's calculate the centrifugal force first. These numbers here. So he's got 23,000 newtons pushing him outwards. And that's going to be balanced by the frictional force, which is going to keep him from sliding off the mountain, which we can also calculate because his car should weigh about 100 kilograms. The coefficient of friction for rubber and road on dry conditions is 0.9. Plugging all that in, we get that the force holding him on that curve is only 8,000 newtons. So let me kind of redo the intro of the show here with how things are really going to work. Very nice. Yay. All right, so Zelda. I can't believe I never done Zelda before. I got Wind Waker HD with my Wii U, and it came with the compendium book thing. So I've been reading that, and Skyloft is one of these things that just boggles my mind. And we always wonder, it's like, how does the thing float? And I mean, there's floating islands in World of Warcraft that just are infinitely pouring water out. Where's the water coming from? I don't even want to get into it. But this one's interesting because we have clouds above it, we have clouds below it, which actually allows me to figure out how high Skyloft might actually be. The clouds that are over it look like they're probably those stratocumulus clouds. The clouds that are under it look like they're probably the nimbostratus clouds, which probably means it's somewhere at about 3,000 meters or 3 kilometers up. I was hoping it was going to be a lot higher and they'd all be asphyxiated or something. Or the birds couldn't really fly that high. It turns out birds fly fragments. It's really impressive. But either way, not so impossible at height yet, but there's one problem. It gets really windy that high up. And wind erosion can kind of be a problem. So let's figure out how long Skyloft is going to last. This actually turned out to be a really hard problem because wind erosion is a super complicated topic. But I'm going to try to boil it down and make it simpler by talking about just on average, let me grab some variables here that we're going to play with this. The wind velocity at 10,000 feet averages 10 to 20 miles an hour, whereas on the surface it averages about 5 to 10, so about half. The weight of wind erosion at the surface, at least for the United States, is about 2.2 to 10 megagrams per hectare per year, where 1 hectare is 10,000 meters squared. So we get that for every square meter you have per year, you're losing somewhere about 0.22 to 0.1 kilograms of soil every year, assuming that you're not generating any soil. Skyloft probably isn't because, you know, there's this magical thing called the conservation of mass. You can't just have mass magically appearing. Well, I suppose okay, this stupid thing flies, but pretend not. Because we also know that things can get lost from Skyloft. If you drop it off the edge, it does not come back because very early on you get to do a quest where you have to go retrieve something from the surface. So it goes away and never comes back. It's a lesson learned. So I'm going to make a kind of fuzzy assumption here. I don't know if it really works. It works in John physics land, but I'm going to say that the erosion is going to scale as a factor of the velocity squared instead of just linear with the velocity, which makes sense to me because it's going to be very dependent on the energy the wind's carrying, and the energy for kinetic is 1/2 energy squared. So I think it's a fair assumption to make here. which means that at 10,000 feet, with the wind velocity being twice what it is, squaring that, it's going to be 4 times the rate of wind erosion. So 0.88 to 0.88 to 4 kilograms per meter squared per year. Great, well now all we have to do is figure out the surface area of the skyloft. That sounds fun. I'm going to make it easy and just pretend it's a cone. So this might be kind of fuzzy numbers, but we're trying to get in the ballpark here. I mean, we're not trying to figure out like the date of doomsday for skyloft. So we have the diameter of it is probably something about 100 meters, about 300 feet. And then the main island is really not that big. It has a big tent on it. It has the graveyard, which always worries me because there's only 6 graves in the graveyard, and there's way more people on Skyloft. And it's supposed to have been there for thousands of years. So is there like 6 positions of honor that they get the graves and then everyone else gets dumped? I don't know. But whatever, this main island is kind of weird. But either way, I'm gonna pretend that it's about 100 meters across, and it's actually fairly shallow. If you're flying onto it, it's probably only about 40 to 50 feet deep. So that's kind of my fuzzy numbers there, which would give a surface area of about 16,000 meters squared and a volume of 39,000 meters cubed. Well, I don't care about what the volume is. I want to know how heavy it is to figure out how long we've got. So a soil density of about 1,300 kilograms per meter squared gives a total mass for that central floating island of about 5 times 10 to the 7th kilograms. So on the lower end, putting this all together, Skyloft has about 3,500 years left, and on the upper end, it only has about 800. Which actually sounds pretty high, except you have to remember, at the end of the 800, you're standing on a speck of dirt going, oh my god. So, I mean, it's not the worst or anything, but also, I just sit and think, man, we were playing Majora's Mask and we only had 3 days, but I guess really there is a time limit in this game too. Who's going to reach it? So anyway, that one actually seems fairly plausible. I wonder how big the island was when it was first lifted up by the goddess, and that probably actually explains why there's like different islands that are all connected by bridges. Anyway, I think this is my last topic for this year. And yeah, water type.
What is this place?
River turns the wheel and makes electricity. If you can hook Pikachu up to it, you might be able to give it a power boost. Of course, right now the river is dry. I have another idea. Pikachu's all hooked up.
Okay. All right.
Pikachu, I choose you!
The Pikachu again. I feel sorry for it, being raised by such a weak Pokemon trainer.
Pikachu, now's our chance to show them how weak we are.
All right, so how much did he really just power up Pikachu? Let's find out. So with a hydroelectric plant, it's obviously being powered by the energy supplied by the water, which isn't there, so it's going to be the power supplied by Ash taking these steps on the water wheel. Really, basically, if he would have fallen down, he would have had a release of potential energy, but he did work to raise himself back up, so each one of those steps is actually equal to the potential energy he would have lost falling down that 1 or 2 steps, because he's taking 2 steps at a time. So potential energy is mgh. The mass for Ash, this is one of these things I really like about anime sometimes. Like, oh, I need to know exactly how much this anime character weighs, and you can actually Google this stuff. So I didn't know this, but Ash weighed 43 kilograms. And each step he took on the water wheel was probably about a foot high. Seems a little high, but we'll go with it. He took 120 steps. I counted it out, unless that was montaged, which it may have been, but we'll see. Which means that his overall energy he gave Pikachu is 15,000 joules. Now, the funny thing about this is the hydroelectric plants are about 90% efficient. That's what's input. There's probably some loss because it was a wood wheel and probably had some friction, but I'm going to ignore that. I'm going to give you the best shot here possible. 90% of that 15,000 means that Pikachu got to store 13,650 joules, And with his Thunderbolt attack, he was going, "Choo!" for 5 seconds. And the joule per second is also known as a watt. Pikachu gave off 2,700 watts. Now, let's ask what would happen if that hit a person. So, the wattage, you can figure out the voltage from that if you know the resistance of the human body. The resistance of the human body is about 10,000 ohms. So the voltage here squared is 27 million, which means the actual voltage is, again, I'm rounding here, the actual voltage for Pikachu is about 5,000 volts. Pretty high voltage. So what is 5,000 volts? Again, I like to try to tell people what these numbers mean. If you came into my talk early on, one of my last segments was I did the over 9,000 mean, and I'm like, 9,000 what? So I started Googling numbers on like 9,000 ergs, 9,000 watts, and different things, and I said to Goku, my favorite thing I found was Goku, 9,000 watts would have powered a funnel cake maker, so I thought that was really cool. I remember that. But I did the same thing here, as I just started putting in 5,000 volts to figure out what that would be. And does anyone know what the #1 search result was? This is how I'm going to end the talk, ladies and gentlemen. So this is a big deal here. The #1 result?
Gigawatts.
No. 5,000 volts, ladies and gentlemen. The #1 search result, and actually the first several pages, is one thing. In 1970,